Hello everyone, welcome back. In this video, we're going to talk about the connection between the two branches of calculus, and this is called the fundamental theorem of calculus. Now, the first part of the theorem states that the operations of differentiation and integration are inverses of each other. Now, the second part will enable us to evaluate definite integrals without needing to use limits. So let's have a look at the statement of the theorem. So suppose that f is a continuous function on the interval from a to b, and we define the function g to be the integral from a to x of f of t dt. Then the theorem says that this function is continuous on the interval from a to b and is differentiable on the open interval from a to b, and that the derivative g prime is equal to f of x. So let's have a look at an illustration of the first part of the theorem. So suppose we have some function y is equal to f of x. And it's continuous on the interval from a to b. Now the function g is defined to be the integral from a to x of f of t dt. And so if the function y equals f of x is positive from the interval from a to b, then g of x represents the area under the curve from a to x. And what the theorem states is that this function is continuous and is differentiable, where the derivative of g is equal to f of x. So we see that the operations of integration and differentiation are inverses, meaning that they will cancel each other when we apply them to the same function. Now, the second part of the fundamental theorem of calculus states that the integral from a to b of f of x dx is equal to capital F of x evaluated at b and a. So this is a shorthand notation for capital F of b minus capital F of a. Now capital F is any antiderivative of little f, meaning that if we differentiate capital F, then we get little f. So in other words, the way that we can determine the definite integral from a to b of some function is to determine any antiderivative of little f, and then we evaluate the antiderivative at the limits of integration. So we take capital F of b and then subtract capital F of a. So we can summarize the fundamental theorem as follows. So the first part states that the derivative of the integral from a to x of f of t dt is equal to f of x. So the operations of differentiation and integration are inverses. So you can think of these operations as canceling each other, leaving us with f of x. The second part of the theorem states that the definite integral from a to b of f of x dx is the antiderivative of f evaluated at the upper and the lower endpoints. So we take the antiderivative evaluated at the upper endpoint, and then we subtract the antiderivative evaluated at the lower endpoint. So let's look at our example that we did earlier. So if you recall, we determined that the area under the function x squared on the interval from 0 to 4 was 64 over 3 squared units. So let's apply the fundamental theorem of calculus to determine the same area without needing to do a limit calculation. So we're interested in the area on the interval from 0 to 4 under the function x squared. And by the fundamental theorem of calculus, we can evaluate this definite integral by finding the antiderivative. So the antiderivative of x squared is x cubed over 3. And then we evaluate this antiderivative at the endpoints, so at 4 and at 0. So we always evaluate the antiderivative at the upper limit of integration, and then we subtract the lower limit of integration. So we substitute 4 into the antiderivative, so that gives us 4 cubed minus 3, and then we subtract the evaluation at the lower limit of integration, which is 0 cubed over 3. And simplifying this calculation, we end up with 64 over 3 squared units as before. Now let's have a look at the second example. We have the integral from 0 to pi of sine of x dx. So let's use the fundamental theorem of calculus. So we're looking for the antiderivative of sine of x, which is negative cos of x. And then we evaluate the antiderivative at the upper and lower limits of integration. So we substitute the upper limit into the antiderivative. So we have negative cos of pi. And then we subtract the evaluation at the lower limit of integration, which is negative cos of 0. So the cos of pi is equal to negative 1. So we have negative of negative 1. And we know that the cos of 0 is equal to 1. So we have minus negative 1. And this will simplify to 1 plus 1, which is equal to 2. And so what this tells us is that the area under the function sine of x on the interval from 0 to pi is equal to 2. And so the shaded region here is 2 squared units. So let's have a look at a few more examples of finding indefinite integrals. So let's start with 3a. We have the integral from negative 1 to 2 of x cubed minus 2x squared, or no, sorry, just 2x dx. So we want to find the antiderivative of x cubed minus 2x. So the antiderivative of x cubed is x to the 4 over 4 minus 2 times the antiderivative of x, which is x squared over 2. And we evaluate at 2 and negative 1. So let's first simplify. We have x to the 4 over 4 minus x squared, evaluated at 2 and negative 1. So we substitute 2 into the antiderivative, which gives us 2 to the 4 over 4 minus 2 squared. Then we subtract the evaluation at the lower limit. So we have negative 1 to the 4 over 4 minus negative 1 squared. So simplifying, we have 16 over 4 minus 4 minus 1 over 4 minus 1. So now let's simplify. We have 4 minus 4 minus a quarter minus 4 over 4. So that gives us 0 minus negative 3 quarters, which is positive 3 over 4. So now let's jump to letter C. We have the integral of from 1 to 2 of v cubed plus 3 v to the 6 all over v to the 4 dv. So let's first simplify the integral. We have v cubed over v to the 4 plus 3v to the 6 over v to the 4. And now we can simplify the powers of v. We have v to the negative 1 plus 3v squared. So now let's find the antiderivative. The antiderivative of v to the negative 1 is the natural log of the absolute value of v plus 3 times v cubed over 3. And we evaluate this at 2 and at 1. So let's first simplify. We have the natural log absolute value of v plus v cubed evaluated at 2 and 1. So we substitute the upper limit, leaving us with the natural log of 2 plus 2 cubed. And then we subtract the evaluation at the lower limit. So that's the natural log of 1 plus 1 cubed. Since 2 and 1 are both positive, we can drop the absolute values. So that's natural log of 2 plus 8 minus the natural log of 1, which is 0, plus 1. So this will simplify to the ln of 2 plus 7. Now let's have a look at letter E. We have the integral from 0 to 4 of the square root of 2x plus 1 dx. So here we want to find the antiderivative of the root of 2x plus 1. Now we need to use a substitution to evaluate the integral. So now let's look at using, or letting u be equal to 2x plus 1. That means that du over dx is equal to 2. And we can solve for dx in the equation. We'll multiply both sides by dx, and then we divide by 2. So dx is equal to du over 2. Now here, since we're looking at a definite integral, we need to be careful about the limits of integration when we are using a substitution. And so one method of taking care of our limits of integration is to write in that these are x limits of integration. So we can write this as the integral from x equals 0 to x equals 4, and then we can perform the substitution. So we have the root of u times du over 2. So now let's simplify our integral. We can take out the constant of 1 over 2. Then we have the integral from x equals 0 to x equals 4, and we will rewrite the square root as an exponent of 1/2. So now we can find the antiderivative. So we have u to the 3/2 divided by 3/2, and then we evaluate at x equals 4 and x equals 0. So now let's simplify our coefficients. We have 1/2 times 2/3 u to the 3/2 evaluated at x equals 4 and x equals 0. And we can substitute back our original variable. So u was equal to 2x plus 1. So we have 1/3 times 2x plus 1 to the 3/2, and we evaluate this at the endpoints of 4 and 0. So here we don't need to write that these are x limits of integration since we substituted back the original variable. So now we'll let x be equal to 4. So we have 1/3 times 2 times 4 plus 1 to the 3/2. And then we subtract the evaluation at the lower limits, which is 2 times 0 plus 1 to the 3/2. So we have 1/3, 9 to the 3/2 minus 1/3 times 1 to the 3/2. So 9 to the 3/2 is the same as the square root of 9 cubed. So we have the square root of 9 to the power of 3. And 1 to the power of 3/2 is still 1. The square root of 9 is 3. And 3 cubed is 27. So 27/3 minus 1/3 leaves us with 26/3.